So can you see the screen now?
Yeah, perfect.
Yeah. So thanks for the invitation, and I said it immediately that I won't be able to travel to Wellington at this point because it's a fall term, and I teach. So so I want to talk about monadic De Morgan lattices, and as you can see, there is a number 2 on the right hand side. So sort of a full disclosure. This is a talk that has some overlap with my talk that I gave earlier in September, and I believe that Fernando heard some of it. So sorry, Fernando, if you recognize a couple of pages from this talk, and otherwise it's okay. So I would like to give some motivations, and this is also a little bit of a self-advertisement. I did some work it was published in 2019 on the fourth logic based on first degree entailments, and I took liberty to modify the standard example, which usually pertains to penguins, to kiwis. So here is the modified version of the example. Tweety is a kiwi, all kiwis are birds, birds fly, and kiwis don't fly. These are the given information, and so if we start to try to draw conclusions from this, then depending on whether we take the all kiwis are birds, birds fly route, or we take the Tweety is a kiwi and kiwis don't fly route, then we get that Tweety flies and Tweety doesn't fly. And of course, it is a problem for two-valued logic because then anything follows. And in fact, in default logic, the sort of the knowledge base or the belief base that is represented by these couple of sentences always needs to be consistent. So there is an insistence on consistency there. So I replaced the two-valued logic with the FDE, and so then the issue is that the data, so to speak, would be just that Tweety is a kiwi, which would be represented by, let's say, a propositional variable k for kiwi. So Tweety is a kiwi. And then the all kiwis are birds would be formalized by its instance in the propositional case, because I would need to formalize this as saying that if Tweety is a kiwi, then Tweety is a bird. And then the default rules would be, again, formalized using some propositional variables. So the point here is that the sort of quantificational structure or the open formula structure in the default rules is lost if one is using a propositional first degree entailment. And I do claim that propositional FDE is better than two-valued propositional logic for default logic, but one could also think that many of the taxonomies that are often expressed by the sort of bare plurals is more adequately captured by monadic predicate logic. And in fact, there are so-called open default rules in which the predicates occur, not instances of the default rules are included. So this is one of the motivation that's sort of why I'm interested in FDE and beyond the propositional part. And of course, I also want to claim that first degree entailment is, as you all know, is central to the main relevance logics that are take to be R, B, T, and E. The ordering here is represents my current view on the interest in these logics. So it's just a subjective ordering of these logic. I don't suggest inclusion here or something like that. I think that FD is a very well understood logic. It has the algebraic counterpart is older than the FD itself. There are various sequence systems, there are tableau systems, semantics, semantic interpretations, there are informal interpretations. So it is important logic. Done in a paper in 1980 showed how to sift out. So how to sort of take two-valued validities and determine whether they are first-degree validities in the form of a binary consequence, which is I think, a very neat idea, especially for those who want to somehow make a two-valued logic relevant, so to speak. And I do claim that FDE, so first-degree entailment, is nowadays part of introductory logic courses. And again, this is a completely subjective statement because I do include it into introductory logic courses. So I'm not sure whether it is true in general, but it is true in Edmonton in some courses. So before I gave the first sort of instance of this talk, so to speak, I decided to give the definition of, sorry, I'm talking about something. So here is the definition of De Morgan lattices. And this is a sort of completely standard definition. It's not a minimal set of equations in the sense that some of the equations can be derived from some other equations, but as you can see, it essentially says that we have a lattice, and the lattice is distributive, and then we have the negation on this lattice, so to speak. So the properties of this structure is that we have a distributive lattice with an order inverting operation of period 2, and it has as a consequence this form of the contraposition and the double negation. And as I said, it has been known before the first-degree entailments were isolated from the pi system of Ackermann or what is interesting, or what is different from the Boolean algebras, of course, is that the contradictions are not all the same or not equal to each other. So it is possible that A and not A is not less than or equal to B and not B. So far, this definition of the De Morgan lattices were not bounded, but for various purposes, I would like to add bounds. And this is, I think it's a completely unproblematic move in the sense of algebra. Maybe for first-degree entailments, as the logic, it might be somewhat controversial because it essentially says that we are going to add the capital F and the capital T constants in the logical sense, and that would be read as the absurdity and triviality in the logic relevance logic terminology. But as I said, I think it's so for my purposes it's needed, so I'm going to add those bounds. So I want to look at the monadic De Morgan lattices, and so here is something that from Helmholtz or Helmholtz. So of course, in two-valued logic, if we define in the propositional case mutual provable implications, so mutually provable formulas A and B, then we get a equivalence relation, which turns out to be a congruence, and so we get a Boolean algebra. And Helmholtz was interested in the, among other things, in the algebraization of predicate logic, and he published papers between 1954 and 9, which were collected together and nicely arranged in his book, Algebraic Logic, that was published originally in 1962. And that is where he introduced the notions of monadic and polyadic algebras. And he, I believe, was always concerned with just classical logic, so to speak, and Boolean lattices, so he wasn't interested in other logics, non-classical logics. And here in the middle of the page, you can see a quote from his book where he says, well, everybody knows that it is useful to make the analogy between, let's say, the existential quantifier and the disjunction, but he points out that the emphasis on the intuitive idea that sum is just an infinite OR, and this is an end of the sentence, the idea is not wholly unsound, but real progress in algebraic logic was achieved only after the realization that the existential quantifier is really a unary operation, not a binary one. Sorry, not an infinitary one. And so he introduced the monadic Boolean algebras by giving series of equations, more precisely on the left-hand side, the equations that are denoted by Q1 through Q5, and they all involve the existential quantifier, so the turned around E symbol. And he pointed out that well, these equations, the first four, can be easily seen to be analogous to the Kuratowski closure conditions. The fifth equation is needed because of the presence of the complementation in a Boolean algebra. And the dual quantifier, so which is definable, of course, using the negation, is the universal quantifier, and it would need to satisfy, if postulated just by itself, the equations on the right-hand side that are Q1 prime through Q5 prime. By the way, let me just note that, of course, some of the equations here are written as inequations, but because we do have the lattice operators, so it's just a trivial rewriting to make them equations. So I will just call them equations even if they have an inequality symbol in it. So Halmos also pointed out that on the background of a Boolean algebra or a Boolean lattice, the Q1 through Q5, so when we have a quantifier on a Boolean algebra, it can be equivalently described by taking Q1 and Q2 and Q6. So this means that the existential quantifier has a fixed point on the least element, and it is monotone, and that is this, what is in red. The Q6 is the sort of a kind of a distribution of the existential quantifier over conjunction or meet, given that one of the components of the meet is itself a quantified object or quantified element. So my idea was to take these equations and take a look at what the analog of these, or what something that would be like the quantifier would be sort of defined. So how it would be defined on a De Morgan lattice. And so I decided to define the De Morgan lattices in the following way. So the same notation, the existential quantifier is going to be the quantifier. And I assume that we do have a bounded De Morgan lattice. And the equations, I labeled them with E, so that I can talk about more easily in comparison with the original equations of Halmos. So they are very similar. The difference, or one of the differences, is that I do want to have all these E1 through E6, and in particular, they are needed, so to speak, in the direction of the inequalities that are left on this slide. So we do have the normality, or that the least element is a fixed point, and the monotonicity, distributivity over disjunction, and we do have the lower left idempotence, and then we have the interaction of the existential quantifier with the negation, as well as is the conjunction. So this is what I came up with. I was looking at what is needed to guarantee that we do have a nice subalgebra. So I needed these directions of the inequalities. And I'm not claiming that I have a proof that without these inequations, something wouldn't be provable. I don't have a proof of that, but the how I was trying to prove I needed these directions. So, of course, it turns out that this is an equational class again. The inequalities, of course, can be rewritten as equations, and so we do have a variety. Of course, we can actually strengthen the 4 of the 5 inequalities. So it is trivial to see that E1 can be stated as an equality because the least element is the least element. And I listed here on this line here the 3 inequalities that actually can be strengthened to be equalities because the other direction can be deduced. So those follow. And so E2 cannot be strengthened, only that remains an inequality. And so that's there. It's just what as it is. It should be rewritten as an equation, so it's not going to be an equality. So if we would omit the least and the greatest elements, then of course we could omit the E1. I'm not considering that because I want to have the least and the greatest element, but maybe for certain interest, it would be interesting to consider that. And so my interest was in what these structures would be, and then to turn to representing them in the sense of the relational semantics as meant in Gaggle theory, so in Dunn's Gaggle theory. So if you look at the definition, and given that we also know what the De Morgan lattice itself is, it is obvious that we have in the terminology of Gaggle theory, we have a bounded distributive multi-Gaggle. The existential quantifier is in fact a very well-behaved operator in this Gaggle. It has a nice distribution type. The negation, of course, as before or as usual, it has 2 distribution types. And in addition, we of course also, so it's not a pure Gaggle, but it has certain additional properties like E2 and E4, E5, E6. So the difference between what Helmut was doing is that I don't claim, and I don't think that it is true that we could omit E3, E4, and E5, and then E1, E2, and E6 would give the same definition. So after I gave the first version of this talk at the beginning of September, I got my hand on a paper that I wasn't able to get because our library only has the hard copy. It might exist actually as a digital book. So this the book is this at the bottom. I mentioned this lecture notes in pure and applied mathematics, volume 203, which was published by Marcel Decker in 1999. But when I came back after the conference, where I finally got the hard copy of this paper by I apologize for the pronunciation, Alejandro Petrovich, I'm guessing. who was at the Department of Mathematics, or who is at the Department of Mathematics in Argentina. And he published a paper on monadic De Morgan algebras in 1999, and he, well, obviously defined monadic De Morgan algebras. And he uses this nebula notation for the operation that he's adding to a De Morgan lattice. And here are the equations that he postulates. He also follows Helmholtz, by the way, and so I'm quoting here what his equations, except that I changed the capital Q's that he is using following Helmholtz to lowercase q, so that again I can distinguish between them. So as you can see, these are the equations that Helmholtz has, although the order is not the same. And so I put here on the right-hand side, you can also see how these labels and equations match up with the postulates that I have. He points out that if we have Q1, Q2, Q5, and Q4, then Q3 follows, which is the distributivity over disjunction or join. And he actually gives a proof of this. He does not postulate the equivalence, so the equivalent, sorry, of what I labeled E4, which would be also the equivalent of the sort of the algebraic view of the dual of the axiom 4. I don't know whether this would be derivable in his De Morgan algebra or monadic De Morgan algebra. I know that so one direction of this equation, so as an two in equations, is derivable if one has Q1, Q2, sorry, E1, E2, E3, and E5 and E6, so the postulates. So it is possible that the other direction is also derivable. So from these equations, what is the E4? I don't see how that would be derivable, but I don't have a proof that it is not derivable. So I'm just conjecturing. And so I put the title is Algebraic Approach. He is interested in the algebras that are the monadic De Morgan algebras and related algebras. So he does mention a connection, sort of in an introduction sort of way to first degree entailments, but he does not sort of makes a close connection, or beyond this mention, he doesn't make any concrete connection to the first degree entailments, and he is interested in the various subvarieties. So in fact, he introduces various types of quantifiers in this paper, which add further conditions to the Q1 through Q5. And he proves theorems about simple algebras and subdirective irreducibles in various classes. And so he's sort of interested in a different way in these monadic De Morgan algebras than what I was interested in, or I am interested in. So what I'm interested in is the Gagos-style representation of these monadic De Morgan algebras or De Morgan lattices. And so here are the sort of, or the conditions. As usual, I'm going to assume that the conditions are universally closed. So for the sake of saving space on the slide, and so everything fits nicely onto one page, I don't have all the universal quantifiers in front of each condition that has an open variable. I assume that X, Y, Z, etc. range over the set of situations. And as you can see, the order relation is postulated to be a partial order. The R is the relation that is going to represent the quantifier. So that is the idea. And I'm using the original Bielinski-Birola notation of G for the representation of the negation. So some of the conditions are sort of very standard. The way I generated the inequalities or equalities straightforwardly suggests that I do need the conditions on f of 5, which is reflexivity and transitivity, and that corresponds to the properties that I had for some of the equations. And the last two conditions are what capture the interaction of negation and the quantifier. So this was E5, and then the last one is what corresponds to E6 in the listing of the conditions. And then the usual evaluation clauses. So the evaluation maps elements into cones of situations, and then the interpretation is pretty standard. The perhaps only new clause, but it's sort of straightforward in the sense of Gagle's theory to interpret the existential quantifier by this V4. And here on the left-hand side, the existential quantifier is the operator in the algebra, and on the right-hand side, it's the meta-language existential quantifier. So given this, I claim that we do have a sort of a soundness theorem, and some steps are sort of summarized here. I wrote out one step in more detail here, but I'm not going to go through this. You can take a look at this 1 through 7 shows that if something is in the conjunction, then it must be also in the existential closure of the conjunction minus the left-hand side element is stripped of the existential quantifier. And as I say here, all the other cases are similarly easy, so they are not necessarily similar, but similarly easy. So that was the soundness. For the completeness, I want to, of course, define the canonical model and canonical frame. And the definition is fairly standard. Again, here the clause that corresponds to the modeling of the existential quantifier via a relation is the definition of the canonical relation in this way, which again, I would claim it fairly standard. And then, of course, one needs to prove a series of lemmas, and I'm just hinting here at what the lemmas need to be. So I labeled some conditions by F1 through F7, and of course, it needs to be shown that those conditions are satisfied given the definition of the canonical frame. So the G, in particular, G is a function and has the required properties, and R is such that it has those properties that were postulated for it. Then one needs to, again, show something that is the analog of the so-called squeeze lemma or primeness lemma. And one needs to show that the canonical valuation, which is defined in a completely standard way, an element is mapped into the set of prime filters that are containing that element, is in fact going to be a homomorphism, and the separation is an old, well-known theorem. So this combines into a completeness theorem or into an isomorphism, into a sub-algebra of the on the set of cones. So we could also add the topology, and so I'm going to quickly outline the addition of a topology. And I'm going to use the notation for the Klopen sets, this notation, for the Klopen cones, this notation. So the O here is indicates the open sets in the topology. And so I claim that we do need to have a Priestley space. So it should be, in other words, so for the purposes of not just to honor Priestley, but also say what this Priestley space means. So it should be an ordered, compact, and totally ordered connected topology. So it's the usual topology that we want to have for a distributive lattice. And then because we do have the additional function and relation on the frame, we also need to have some further conditions. So F9 captures here the idea that the result of the operations that are defined on open Klopen cones is going to give us a Klopen set. The tonicity is going to follow from the properties of the relation and the operation. So this is the F9, the two parts of it. The 10 and 11 are going to be further needed because of the way how we, so again, for the R here, the condition actually is the complement of R. And we want to change also the valuation. So I denoted this by V0. We want to actually map the elements of the algebra into, as I said, Klopen cones to start with. And then we are guaranteed to get Klopen cones by the definitions. Furthermore, we might want to also get nicer topological matches, so to speak. And if we consider, so I take it that between the algebras, we sort of know what a homomorphism is between two monadic De Morgan lattices, but we want to say what properties the maps between the frames should satisfy. So let's assume that psi is one of these maps that we want to have between F1 and F2, where of course F1 and F2 are these topologically enhanced frames for monadic De Morgan lattices. And then we want to say that, first of all, of course, this map should be order preserving and continuous. So it should be like to start with as the maps between Priestley spaces, but we also want to have these 4 additional conditions to make sure that the maps are going to behave well. And if we do all this, then we can, of course, define the canonical frame and canonical model, so to speak, and the sub-basic set. So I'm continuing here the numbering from some previous pages. So 4 is the definition of a sub-basic set. So with respect to that, there is absolutely no change. It's just like the what we have for the Priestley topology on the distributive bounded distributive lattice. And given, so we need to again continue with proving something further. So we want to show now that the homomorphism is actually into the Klopen cones, not just up into cones of situations. We need to show, of course, that the topology is a Priestley topology. We need to show that these additional conditions hold for the relations and topology, relating the topology and the relations and the G function. And then we can show that if we have a monadic De Morgan algebra, then we take the frame or the topological frame of that algebra, and then we take the algebra of that frame. Then we have an isomorphism. And so this is a slight strengthening from the completeness theorem because of the fact that we actually precisely delineate the image of the canonical valuation. But we can also do the dual thing, so to speak. So we can start with a frame, a topological frame for a monadic De Morgan algebra. We can take the algebra of that and then take the frame of that, and we can show that we do get a homomorphism between these, and furthermore, the order and the two other relations are also preserved or respected by this homomorphism. And so this is going to give us the sort of relationship between the objects, and we can go further. And as I said, if we also add those last conditions, then on the previous page, then we can actually show that the homomorphisms and these maps between the frames also satisfy a 1-1, or there is between them a 1-1 correspondence. So the bottom line is that everything works out nicely. And so that's the end of the content. So thank you for listening and allowing me to give a talk in this workshop. And here are some references.